At least I can hear you. At least I can hear you.
We can start now. We are live.
Okay. Welcome, everyone. Thank you for joining us for today's webinar. My name is Adriano Andricopulo.
We are live.
Okay. Welcome, everyone. Thank you for joining us for today's webinar. I'm a former president of the Brazilian Chemical Society, 2014 to 2016, and I will moderate this webinar and discussion. First of all, I would like to welcome our special guest today, Professor Regina Palkovits from the RWTH Aachen University in Germany. On behalf of the Brazilian Chemical Society and our current president, Professor Romeu Cardoso Rocha Filho, I can truly say that it's a pleasure to have you here with us today. Regina studied chemical engineering at the Technical University of Dortmund from 1998 to 2003, spending a semester abroad at the Lafayette University in the US. She received her PhD from Max Planck Institute for Coal Research in 2006, and then spent a year as postdoc at Utrecht University, Netherlands. In 2008, she became group leader at Max Planck Institute for Coal Research, and in 2010, associate professor at RWTH Aachen. From 2014 to 2021, she was executive director of the Institute of Technical and Macromolecular Chemistry at RWTH, where she has been a full professor of heterogeneous catalysis and technical chemistry since 2013, and currently is chair of the heterogeneous catalysis and chemical technology. The title of her presentation today is Contributions of Chemistry to Sustainable Development, a View from Germany. After Regina's presentation, the audience will have the opportunity to ask questions. So please send your questions at any time during the presentation via the YouTube chat. And I promise to keep an eye on the chat window. And now, without further ado, Professor Regina, the floor is yours. Thank you.
So thank you very much for the kind invitation and for the welcome here. It's also a pleasure from my side to talk to you today. In best case, you should see my slides now. Is that working? Wonderful. Then I will start. So what I brought to you today is a German perspective on the contribution of chemistry. And so I will give you a short introduction of the major aspects I would like to tackle. And then later in the talk, I will highlight 3 showcases from large flagship projects which are currently ongoing in Germany to highlight some of the contributions which chemistry can bring in the sustainable development. Now, first, let's set the scene. So currently, we are still in the fossil age, and that means that we use fossil resources such as gas, oil, and coal to basically produce power, to produce our fuels, and also to produce chemicals. Now, we are aware that that may not be sustainable for the future, and we have to change this figure somewhat, and the possibility to change this figure could look like this. So we are aiming for closing the carbon cycle. So we would produce our energy, our power, by different means of sustainable energy technologies like a solar or wind power, and that gives us access to electricity, so green electrons, and that also enables us to produce hydrogen in a green manner, for instance, via electrochemical water splitting. Now, combined with renewable carbon sources, such as biomass, CO2 from air, and also recycling, for instance, from plastics, we could then produce fuels and chemicals in a hopefully sustainable manner and achieve overall closed carbon cycles. Now, this overall vision has some challenges, and I guess chemistry is here the right key element to solve them. So if we look in the current setting of chemistry we are used to do now more than 100 years, then our value chains are based on methane, CH4, on hydrocarbons based on oil, and on coal. And all of them are composed by carbon and hydrogen. So these hydrocarbons basically are non-functional. And so to utilize them in different value chains, we need to oxidize. So we have learned to work with non-functional compounds in chemical industry and to basically functionalize them. And we do this in processes usually at very high temperatures because the compounds are easily evaporated, brought into the gas phase, and then we functionalize them. We have large deposits, and that gives us access to these resources in a way that we can use economy of scale and build large-scale production plants. And we have a constant supply, and so we are able to go for stationary processes. So basically, that is the situation we have extracted from this chemical setting we have seen the last 100 years. So based on fossil resources, we have basically developed thermocatalysis, so chemical transformations with the help, often with the help of a catalyst at elevated temperatures in the gas phase. And we do this transformations in a steady state, so under the same reaction conditions all the time, feeding in something and getting the product all the time out. And we do it in huge production processes because the supply is not a problem. Now, that figure changes completely when we switch to renewable carbon sources. So here we have really to tackle and master complexity. So if we look, for instance, into lignocellulosic biomass, so the residues of food production, which are not in competition with the production of food, we have a material which is very rich in oxygen functionalities. Just some examples given over here for cellulose and hemicellulose. The same is true for CO2. CO2 is the highest oxidized form of carbon. So we have a lot of oxygen in this molecule, and in addition, it's thermodynamically absolutely stable. So it's a very inert compound and not so easy to transform. And then another challenge now occurring is that also plastic could be a very good feedstock for future value chains, either to directly recycle back into the same application, so to create directly closed loops, or to transform it back into the building blocks or other chemicals which may be used. But looking in all of these resources, we have oxidized carbon. And now the technology we need from a chemistry point of view is defunctionalization and reduction. So that is the opposite to what we had before. We have now distributed and diverse resources, so it's not all found on one spot. So we need maybe modular plants, much smaller, and we need technologies which are scalable. And finally, I mean, the supply of biomass and also of other resources is now fluctuating with time and season, especially also related to the renewable energy supply. So we have fluctuating quantity and quality of feedstocks, both in the carbon source and in the energy source. So we need robust and potentially even dynamic operation in the future. So first, a look on biomass as a potential resource and the chemical challenges associated with it. I said already, lignocellulose may be a very interesting resource because it is not in competition with food production, and it brings a lot of nice chemical functionality to synthesize various chemical compounds for polymer industry, for biofuels, and so on. It's a composite material, so it's quite demanding in terms of production processes. So you first need to cleave the different fractions, So to get the cellulose, hemicellulose, and lignin fraction, and then to further treat them. And the major difference, as I have highlighted already, is the high oxygen content in these compounds, which is also illustrated over here. So if you rationalize the composition of biomass in terms of a diagram showing the hydrogen to carbon ratio compared to the oxygen to carbon ratio, you see that all the chemical feedstocks we are used to use in today's chemical industry are down here. So methane, crude oil, coal, gasoline, they are all over here. So they have close to no oxygen content, while the alternative biomass feedstocks possess a very high oxygen content with close to 1 oxygen per carbon atom. Now, that also has a very direct impact on the energy density of the compounds if we think about biofuel production or the production of chemical energy carriers, so the storage of chemical energy. Here, our current fuels are very, very efficient. So they have a very high both volumetric storage capacity and gravimetric storage capacity. So the amount of energy per volume and per kilogram, which is contained in a certain compound. So you see our current compounds, diesel and gasoline, are very up here, while a plant material is pretty much down here because there is so much oxygen in it, which reduces the energy content. And so novel fuels like ethanol or also methanol, which may be produced in the future based on CO2, are somewhere in the middle. And also hydrogen is pretty much down there, and that is majorly due to the storage issue. So hydrogen has a very high energy content, but not for sure not in terms of its gravimetric and volumetric energy density. So we need sufficient means to store the hydrogen somewhere. And you see also some examples of other energy storage in the graph over here. Now, one word to CO2 before we enter the case studies I wanted to highlight here. So that is a nice study by my colleague, André Bardo, who was at Aachen University and unluckily went to ETH Zurich lately. And they analyzed the different kinds of CO2 sources which are available in Europe. And here you really see this picture of distributed resources. So if we want in the future to valorize CO2 as a feedstock for chemical industry, for closed carbon cycles, that is all the places where we find the CO2 and where we would basically need to transform it either directly or from where we would need to transport it to more centralized places. In addition, of course, to this industrial sources in power plants, pulp and paper production, steel and iron, concrete, you also have the possibility to do direct air capture. So to get the CO2 wherever you want from the surrounding air. However, at the moment, that is a technology which is not ready yet. And it depends very much on the electricity mix you have available in the country if direct air capture of CO2 makes sense. So imagine Germany. So we have still, I would say, a pretty dirty electricity mixture. So lots of fossil energy providing our electricity. And if we, with this electricity, drive a direct air capture today, then we basically produce more CO2 in the production of the electricity to drive the direct air capture, then we can separate with the technology. But in other countries that is already pretty much different, and also Germany is very, very intensively trying to change the energy mix to renewable energy technologies. Now, as I have said, I would like to talk about 3 case studies with you. So I would like to highlight Power-to-X technologies for CO2 usage, and there discuss a potential Power-to-X based fuel. I would like to talk a bit about hydrogen storage and the chemistry behind it, and a bit about biomass valorization and the possibility to directly integrate renewable electrical energy in the transformation of biomass. So basically to use all the know-how of electrochemistry to make nice products over here. Now, the power to X phase has found a lot of attention in Germany lately, and there has been so-called Copernicus projects installed now around 7 years ago, and they are meant to run for 10 years. So it's 4 different Copernicus projects, and every large-scale Copernicus project is running for a total of 10 years. And they are focusing on the different aspects which we have to tackle when it comes to the transformation into an overall sustainable energy system. So Ensure is looking into the grid structure and how we can connect all the different sources of renewable energy with a proper grid and stabilize it. Synergy is looking into heavy energy demanding technologies like steel production and how they can be modulated in a dynamic fashion to maybe modulate production according to energy availability. Then we have Innavi. Innavi is trying to find an optimum way to couple the energy networks of heating, electricity, and transport. And Power to X, and that's the part I would like to talk about. And in Power to X, we are looking for value chain design to come from water and CO2 as ultimate sources up to novel energy carriers or fuel compounds and also other products. Now, a little bit of chemistry, of course, is needed because we have chemistry as key enabler. And so we have a look here on CO2 as a resource. And thermodynamically, CO2 is very low in energy. So it really does not want to be transformed. So what you need is for sure an energy-rich reaction partner to move it up and produce a product which is a bit lifted in energy, so to reduce the carbon a tiny bit. There is also an additional barrier, a transformation barrier, which can be reduced significantly with a suitable catalyst. And that's usually the game. Now, this energy-rich reaction partner can be different things. It can be in chemistry for polymers, epoxides, and it can also be hydrogen or even electrons directly. All of them are potential energy-rich reaction partners. Now, if we look into the reduction raw of CO2, and we always add one hydrogen molecule, then that is what you see over here. So we go from CO2 with one hydrogen to formic acid. So that's the direct combination of CO2 and hydrogen. With the next hydrogen molecule, we get up to formaldehyde. Then another one brings you up to methanol. And with the last one, the fourth one, you are at methane, so synthetic natural gas. You also see that there is a little bit of drawback if you go to very high degrees of reduction for your carbon. So if you go all the way up to a synthetic natural gas, you have invested 4 hydrogen molecules, but you have lost formally again already 2 of these hydrogen molecules in the release of water. So a lot of the electricity you have beforehand invested to produce hydrogen via water electrolysis is lost already. Nevertheless, is a very potent technology which is heavily discussed to have synthetic natural gas because we have the natural gas grids available and it's well-established technology. Now, what I would like to talk to you about is an alternative fuel compound which may allow clean combustion, which is heavily discussed, especially for diesel vehicles, but for heavy duty, for instance, that may on a long term still be needed because of the high energy density of diesel-like fuel molecules. So I would like to introduce you to this molecule over here, DMM, dimethoxymethane, or also called OME1. So that is basically the structure. So you have no carbon-carbon bond. So you have a CH3 group, 2 oxygen, a CH2 group over here. And so if we want to produce it, usually what we do is we can transform our CO2 to methanol And we combine basically the methanol with a formaldehyde, and we gain this structure over here, which is formally equivalent to the formaldehyde level, at least this carbon over here. So this molecule can be produced based on CO2, and I will show you a bit more about this in a minute. But first, I would like to motivate why this molecule could be an interesting one for application. And so there is the Copernicus project Power to X, which in the first phase looked into this OME1 molecule, and the ministry, the BMBF funded Namosin project looking into this molecule, and also some other large-scale initiatives. And they all are motivated by the fact that the OME1 and also longer OMEs can be produced based on CO2. And they are not only compatible with the diesel infrastructure, but they also can significantly reduce the usually problematic NOx and soot emissions associated with diesel combustion. So I brought you 2 slides on combustion technology from my colleagues at the Chair of Combustion Science at Aachen University. And so what we look at here is the behavior of the fuel in typical engine tests. And so we do an OME1 blend with normal diesel. And so that is what we do over here. So we mix more and more OME in our diesel from 0 volume % up to 100 volume %. On the other axis, we have the oxygen content, which is associated to this. So it's clear the OME1 brings some oxygen in the molecule. And then we have plotted over here the cetane number. And you see that up to a content of around 35% of OME1, we still fulfill our currently valid norm concerning the cetane number, which the fuel should fulfill. So we still are above 50. Now, we look at the combustion properties of such a fuel. And that's also kind of interesting chemistry. So combustion chemistry, I would also argue, is also part of chemistry. What we see over here is the emission properties of such a blend. So we have the pure diesel over here. And what you have plotted are the NOx emissions over the soot emissions. Sorry for the German title. I thought I changed it, but obviously there was a problem. So here is the soot formation. And here is the NOx emission. And so with normal diesel, we can optimize our engine operation to have either pretty low NOx formation, but then we have a lot of soot. Or we go for low soot emission, but then we have a lot of NOx. Now, we add a little bit of OME and we see that changes. And for the 35% which still fulfill the current legislation, we are already at pretty much optimized conditions. So we suppress soot emissions significantly. And so we have a much wider operation window to also get our NOx emissions to a minimum. And if we go for a 100% OME1, you see that soot formation is completely suppressed. And one chemical origin is that we don't have any CC bonds over here in this molecule. So soot formation is very much hindered. The other reason is the different evaporation and combustion behavior, and that I show you over here in a little video. So it will run again. And you have to understand what you see. So we look now in the engine chamber where the fuel is combusted. And so what you see over here with this yellow frame is the liquid penetration. So that's how much we can spray the liquid in the engine. And then around it, the red frame gives you how far the vaporized compound can reach until it is finally, and that is what you see in the very intensive color, combusted. And now in the direct comparison, what you see is that the yellow for OME1 is much smaller. So it means the liquid is much faster transferred in the gas phase. So evaporation is better, is more efficient. The second is the red area is longer So the vaporized OME has much longer time in the chamber to mix with air before it is finally combusted. And that leads to a very clean combustion and is a major chemical background of the clean properties of the OME1 fuel. Now, when we look now in the chemical production of this compound, and we need a bit of chemistry to really show that it's a big contributor here. So we look in the established route. So what we could do and what is state of the art today with the first plant running in Iceland would be CO2 hydrogenation to methanol. And we use CO2 from a point source or from direct air capture, and we use renewable hydrogen from direct water splitting with green electrons. So we have green methanol available, but then for the production of our OME1, we need to oxidize part of this methanol back to formaldehyde to, in the last step, combine methanol and formaldehyde to this molecule over here. Now, I show you a measure for efficiency of this transformation route, and that is a Sankey diagram. That's an exergy diagram. So you may have heard of exergy in thermodynamic classes. So exergy is majorly the energy which is lost from the process due to heat release, water formation, so undesired loss of energy, which cannot be retained in the molecule where you want it to be, because we want to produce a fuel. So we want to keep as much of the intrinsic energy of the compounds in the value chain as possible. And so for this value chain, what happens is with the methanol production, everything is fine. But then we have here the methanol, which is partially oxidized to the formaldehyde level. And this oxidation means that we produce water. I showed you the CO2 row, and to get formaldehyde, we basically lose the hydrogen in one water molecule, and that's a loss over here. So we have a big loss due to this pathway where we first reduce CO2 to methanol and then oxidize it back, which is not very clever somehow. But it's a robust process which is already on a very high technology readiness level, but it has some optimization potential. And my colleague, Jürgen Klankermeier and Walter Leitner, my colleagues, developed an alternative route using chemistry, using homogeneous catalysis in this case. And so that's the route I just showed to you. What they do instead is that they found a catalyst which can now directly take the methanol, so methanol was fine, and combine it not with a formaldehyde, which we need to get from oxidation of methanol, but can directly integrate a CO2 molecule with hydrogen into this methanol and produce the OME1. So we get rid of this formaldehyde production. That's what you see over here. We get rid of this exergy loss. That's what you see over here. And the overall maximum energy efficiency of the process is rising 12% because we have now done clever design of value chains and used our chemical know-how to basically save all energy in the process, as much energy as possible. So we go for a hydrogen efficient pathway. That is also something which is now heavily investigated in terms of economics. And so that's a slide which I also wanted to show you here. Of course, new technologies have it always difficult to enter the market. So if you look over here, you see the hydrogen price in $ per kilogram and the potential costs of DMM production, so of this OME1 production. And you have here the price of fossil diesel, which at the current situation, in fact, we would need to correct to be somewhere here too, maybe around. And then you have the potential costs of the different technologies with this oxidative traditional route over here, and with the long-term reductive routes over here. So they are much less dependent on hydrogen, so you need less hydrogen, so they have the potential to be cheaper, but they still need some time to become ready to market. Yeah? So with this, I would like to change gears and have a look onto hydrogen. So you saw already that in many of the value chains where we have to closed carbon cycles, we need hydrogen as a reductant to basically uplift CO2 and also to prepare other chemicals. Now, hydrogen technologies are another very much focus area of German research at the moment. I just brought selected examples, so it's far from comprehensive. So we have, for instance, a large-scale product funded by the Federal Ministry of Education and Research. It's called H2Giga. So that looks into large-scale cost-competitive hydrogen production via water electrolysis. We also have a future research cluster hydrogen, which is hosted by Aachen University, where we look into new hydrogen technologies like electrochemical ammonia production and hydrogen purification by electrochemistry and so on. And there is a new research institute formed only focusing on hydrogen technologies. It's a Helmholtz cluster HCHQ, which is anchored to the Jülich-Helmholtz Center and which is basically focusing on hydrogen technologies. And I brought you one of these technologies. So you heard already hydrogen can be produced via water electrolysis. And there is a lot of chemistry also in water electrolysis. You need proper electrodes, proper electrolytes, all true. But I wanted to talk today about the next step. So what if you have your windmill offshore, maybe close by, you have your electrolyzer, and then you have your hydrogen. How do you get your hydrogen from A to B? How do we get the hydrogen from the place where the energy is cheap and easy to make in a green way, shipped most probably in the form of a chemical energy carrier like hydrogen? How do we get it transported? And so hydrogen itself is not an ideal compound to be transported around. So you need to pressurize it to 700 bar to have an efficient transport. So a very intensively researched idea is to bind it to chemical energy carriers, so-called liquid organic hydrogen carriers, LOHCs. That's what you see here. So liquid organic hydrogen carriers. So that is chemical compounds which can bind in a reversible manner. So they can bind and release hydrogen on a demand in a very efficient way and in a high amount. One of the easiest hydrogen carriers would be the formic acid, which I have introduced. But formic acid is pretty corrosive and it's also not so easy to store. So a technology which currently is intensively discussed in Germany is the LOHC technology using so-called dibenzyltoluene. That is an aromatic compound, and I show you that chemistry in a second. And this compound enables high storage capacities, and it is liquid at room temperature. And you don't need any pressure transportation. So you could basically ship your LOHC, which is filled with hydrogen. So you basically charge it with hydrogen. You can ship it to the place of demand where you can use the hydrogen, and then you basically transport your carrier back and it's loaded again. So this chemical can serve as kind of a hydrogen battery as an easy illustration. So the LOHC has a fuel-like character, so it can be used in the typical fuel infrastructure. It can be transported by ships, trucks, and in tubes. It can be pumped around. You have this return concept like in batteries or bottles. So you fill it again, and it can supply hydrogen on the spot where it is needed. Potentially, it offers local and global zero emissions. Now, what is the chemistry? And so there is different kinds of compounds discussed. So in Japan, there is a lot of attention on toluene. And here, this technology, which is favored at the moment in Germany, looks in this perhydrobenzyltoluene. So that is this molecule over here. So this is the fully loaded state. So we start from benzyltoluene, which is the unloaded stage. And then we hydrogenate it, and so we can put 6 hydrogen atoms in this molecule with an appropriate catalyst. So again, chemistry heavily involved. We do so at around 200, 250 degree and elevated pressure. So we hydrogenate our compound. Now it's loaded, and that's what you see over here. So it's liquid at room temperature. It has a huge storage capacity, and it can be brought to the spot where the hydrogen is needed. And at this spot, you then dehydrogenate at basically atmospheric pressure, maybe even reduced pressure. That's the current topic of research, and around 300 degree, and you get pure hydrogen released. And so what is currently going on in Germany is that there is indeed a first industrial storage unit implemented in Dormagen, Germany. So it's a storage plant with 5 tons per day. And so that is the currently world largest LOHC storage plant. It can overall produce 1,800 tons of LOHC, stored green hydrogen per year. So it fills 50,000 tanks, 10,000 tanks filling for a hydrogen train could be made. And there is partners such as Hydrogenius, LOHC technology, which is the startup company, which grew tremendously in the past years, and Covestro and Vopak, and that is supported by the state of North Rhine-Westphalia. So the plant will be commissioned and start of operation is in 2023. And the hydrogen which is delivered there can be used in different industrial sectors. So in the Copernicus project, for instance, glass production is in the focus. It can also serve for hydrogen fuel cells. So you don't need a high pressure hydrogen storage at a hydrogen fueling station, but you can on demand release the hydrogen from the LOHC to feed your hydrogen car with hydrogen over there. Under development and also pretty promising is a direct on-board use of LOHC, so that you really can use this as a fuel itself. So for heavy duty applications, and then have internally the dehydrogenation to release the hydrogen. And a lot of chemical, especially electrochemical technology development is needed over here. So now I would like to come to the last example, and that is from the biomass field. So Germany also has a national bioeconomy strategy. And so there is various initiatives going on. And I brought you something from our Fuel Science Center at Aachen University. And so I brought you a tiny bit of my own research also. And so the Fuel Science Center tackles with the transformation of renewable carbon sources and renewable energies, and is one of the DFG funded clusters of excellence in Germany. And so the idea here is that we need efficient value chains along the transformation of the different resources to get to fuels and chemicals. And that means that we need to be aware that maybe not one of the chemistry disciplines is sufficient, but we need to team up along the value chain. So maybe we need a mixture of chemo, bio, and electro catalysis to do an efficient transformation. And that's what we demonstrated lately. And so I show you this example over here. So what we take is a biomass source. It can be glucose, but it can also be waste biomass. It can even be, and my colleague recently demonstrated it, so that's from the Blank group at Aachen University, that's a biotechnology group. They demonstrated even using plastic waste as a carbon feedstock. So they transform this diverse sources of carbon in a biocatalytic approach in so-called HAAs. This is hydroxyalkanates, so comparable to rhamnolipids if you are from the field. So what you have here is acid groups at the end, and they are bound via an ester group. And you have here carbon chains, which can be tailored in length, and that's very nice. So we can basically order at our biocatalysis colleagues which chain length we would like to have. And so in this case, we wanted to have something which is suitable for the kerosene range to prepare biomass-based aviation fuels. So now then we do a bit of chemocatalysis to hydrolyze it. So we have the individual chains, and then we use electrochemistry to get a fuel. And we use a very traditional electrochemistry, which some of you may have seen in their chemistry studies. So here is an acid group, right? And so if you remember, maybe there is a so-called Kolbe chemistry, which is 150 years old, and now we can use it back. So this Kolbe chemistry enables you to transform a carboxylic acid in electrochemistry. And what you do there is that your carboxylic acid is adsorbed on the electrode with a carboxylate group, and then it's cleaved. So the acid group is cleaved off. So here, and then CO2 is released, and the rest of the chain is staying in there. And this chain can then do two different things. Either two chains meet and form a dimer, or the radical undergoes a further electron supply, and basically you go in the non-Kolbe route and you can form olefins. Also other products, but especially olefins are interesting. An additional note here, this Kolbe chemistry is carried out at the anode in electrochemistry. That's interesting because the hydrogen we produce in electrochemical water splitting is produced at the cathode. So, I mean, at the anode, at the moment, we would produce oxygen, but maybe we have more clever ideas in the future what we do on the other half cell in hydrogen production. So what comes out over here is if we do electrochemical transformation of this 3-hydroxydecanoic acid, what our nice colleagues from biotechnology prepared with electrochemistry, then the dark blue is the product you get. So we get a product mixture. So this different compounds over here. So I would say 5 compounds in a larger quantity and then 2 others in a smaller content. And overall, we get 100% conversion and 95% yield. It's a mixture, yes, but it's a very efficient transformation. And this transformation even works. So now look at the light blue. If you don't use purified feed, but you use the fermentation broth of your colleagues, they really take out of biocatalysis, and you do the same electrochemistry without any purification. You lose a bit in yield, it's true, but you have a direct coupling of biocatalysis and electrochemistry for a very interesting potential oxygenate mixture with application in fine chemistry and in fuels. And we tested for the fuel applications. I show you in a second. What is nice also on this technology that is the very benign reaction conditions. So it's at room temperature, of course, in methanol solution with a carbon anode and a titanium cathode. So it does not at all require any noble metals. So that could really be an interesting one. Now, what about the fuel properties? So we took the 5 major compounds and created an artificial fuel mixture according to the composition we got in electrochemistry, and tested it with our colleagues in combustion engineering for the fuel properties. And you see that our C9 product mixture is in all relevant properties, and there is much more in the article to find if you're interested. In all relevant properties, it fully fulfills the standard norms, so it could be used today in an engine without any problem. So last but not least, last slide on science, I owe you an example for dynamic operation. And that's also something which is very heavily investigated in different initiatives in Germany. So how can we start doing chemistry in a dynamic fashion? And I brought you now the example for the Kolbe chemistry. So we do a Kolbe electrolysis of succinic acid ester that leads to an interesting product for polymer production. And we do this electrolysis using once a stationary energy supply, so a constant current density. So the number of electrons per time is constant. And once we took a windmill profile and injected the electrons according to the windmill energy profile, which we took from the web. And so that's what you see here. In both cases is in total the same amount of electrons which goes into the reaction. Is in both cases 1 Faraday equivalent. And now here you see the result. So we see the product selectivity. That's the first bar in both cases for constant supply and for variable supply. And you see the current efficiency, which is basically the selectivity of electrons doing the right thing in the transformation. And also this stays the same. So constant and variable operation both lead to the same result. Variable one even looks a bit better. So that may be indeed a way to go. So I hope with this, I could give you a little flavor of the initiatives in Germany and the contribution of chemistry as key enabler in power-to-X technologies in the field of hydrogen and in the future bioeconomy. And with this, I would like to thank, of course, my research group. So that's some recent photos. Here we were hiking last summer at the 3 country points. So when you ever come to Aachen University, don't miss the 3 country point. So here is basically the border between Germany, Belgium, and the Netherlands. And so you can touch 3 countries at the same point in your life. That's also interesting. I would also like to thank the funding agencies, especially the ones I've already named during the talk. And I would like to thank you for your attention. And I'm happy to answer the questions which are coming now.
Hello.
Hi, hi.
Are you there?
Shall I leave the screen share on or shall I switch it off?
It's up to you.
So I will stop it. If you need it, I can get it back. Good.
Okay, thank you very much for your wonderful presentation. Very nice chemistry and very hot and special subject for all of us. So thank you very much for the presentation. We have a few minutes for a few questions, if it's okay for you.
Sure.
Is biodiversity one of our best allies in sustainable development? Could you please comment on this topic?
I mean, biodiversity is basically the foundation of a healthy environmental system. So you will not be able to grow plants if you lose too much biodiversity. So we are also heavily looking in what biomass-based streams are useful and what the impact, also the long-term impact of preferential utilization of different plant material is. So ideally, we would need technologies, and here chemistry plays a role, which are robust for different streams. So we are happy with whatever plant material we get, so we can keep all the biodiversity. And the chemistry is responsible to make basically the funneling into our selected desired products for our daily use.
Okay, good. Which are the perspectives to achieve the SDGs, which are the Sustainable Development Goals by 2030 in terms of reduction of the used fossil fuels?
That's a very difficult question. I mean, you can take hours about this, and politicians do talk hours and hours about this. And I mean, if you follow the political discussion, there is always a conflict between available technologies and their price and the acceptance of the public of new technologies and their costs. So in principle, we have most of the technologies ready to leave the fossil fuels behind us, but we have not the infrastructure set up properly to do it just ad hoc now in the next week or next month. So we still will need a transition period, and 2030 is very close. Yeah. So if you look in a typical chemical engineering company, if you have a new technology developed in the lab, it takes 20 years to get it to a plant. Yeah. Already the building of the plant takes 3 to 5 years, depend on the size and the scale. So what we see is the fast entrance of renewable energy technologies is the most important driver that has to be done, and that is heavily driven forward in Europe. One has to understand what the role of which country is. So Germany has not a very easy life with building up on its own sufficient renewable energy supply to cover our electricity need, for instance, just as an example. So it's very difficult for us. So most probably there is countries such as Germany, which will remain net energy importers. So we are now an energy importer. So we import energy in form of fossil fuels, in form of electricity from other countries, and that will remain most probably true in the future. There is nice spots in the world and around us where electricity can be produced and can be transformed into chemistry. And the clever transportation and valorization in chemical industry is what we need to look for. So what is the interface between the energy sector and the chemistry sector to reach fast defossilization of all the areas where we need the carbon? Yeah, so there is applications where you need carbon. A polymer without carbon is pretty difficult to produce. So there we need defossilization. We need renewable carbons and renewable energy. And there is areas where we don't need the carbon, that's electricity. And there we need to do decarbonization. So get rid of carbon containing compounds, get rid of combustion processes as much as possible. That's not a perfect solution, but that's what I can contribute to this very difficult question.
Oh, yes, I agree. It's a very complex matter and the whole situation. But we have here a more specific question for you regarding the alternative route to DMM. What's the role of the ruthenium complex catalyst and the Lewis acid aluminum?
Yeah.
And can the transformation be carried out with other catalysts and Lewis acids? Is the mechanism already elucidated?
The mechanism is, so I'm not someone from homogeneous catalysis, but I will try to explain it as good as I can. So as far as I understood the research of my colleagues from homogeneous catalysis, what is happening is that the ruthenium complex, so it's the ruthenium triphos, you have ruthenium bound to 3 phosphorus atoms in this ligand. And so this is responsible for the CO2 reduction in situ to the formaldehyde level, yeah, to the it's formed to the formic acid level. You form the methyl formate, so the ester of formic acid and methanol is formed. And then this methyl formate is reduced further. And that is how you basically then get to the DMM mechanistically. And that so the Lewis acid is responsible for the condensation reaction, so for the metal formate formation. So the complex does CO2 hydrogen to formic acid, the Lewis acid does basically the esterification, and then the ruthenium catalyst does the next reduction, and the Lewis acid does the second condensation. That's the mechanism which is proposed at the moment, and there is a lot of proof for this. In the literature is also one example on a solid catalyst, the ruthenium in a zeolite, which demonstrated also direct DMM production. So there is different catalysts which may be an option, but the heterogeneous one was much less active, as in many cases. So in many cases, homogeneous catalysts are pretty good, but they are difficult to scale in industry. Yeah, so there is many routes out, and I think a lot of development will happen in the next years. It's still a very new route. Yeah, it's new chemistry which is now evolving when we try to look for hydrogen efficient reaction pathways. So you really need to rethink how you can do the transformation in a way that you retain the energy in the molecule and don't waste all the hydrogen which you invested in oxidation processes.
Okay, next, the process of making ethanol from sugarcane generates a lot of bagasse. Do you think that the extraction of lignin from this bagasse is a good alternative to be used as an energy generator?
I mean, chemically, lignin is a very difficult one. So to use it for energy production is a solution. I mean, many people still dream to use lignin in a chemical way, right? To make even use of it as a resource for aromatic compounds, especially. Yeah, but sure. I mean, in a biorefinery, in the future. You will have different streams. So you will have some easy streams which can be transformed in a straightforward matter to product. So you can take the cellulose stream, you use some clever enzymes to get your glucose, then you produce bioethanol. There is hopefully a CO2 capture because, I mean, out of the 6 carbons in your glucose, 4 end up in the product and 2 end up as a carbon dioxide. So there's a lot of carbon dioxide in bioethanol production, which is a very nice local CO2 stream to be used. That's also something what one should look at. Then you have the lignin, the bagasse, especially in the bagasse, which could be used for energy or for fine chemicals. Then the technology can be more expensive. And you have all the hemicellulose, and we also need clever ideas for the hemicellulose. And there are some nice technologies out also to produce bioethanol from the hemicellulose, or to go for compounds like ethylene, propylene glycol, which are also base chemicals. So it is, as we have it today in refineries, we have streams and we need coupled value chains. Otherwise, we will not reach overall cost and energy efficient technologies. And cost and energy efficiency is also an important part of sustainability.
Okay, well, time's up. To close this webinar, I'd like to ask you a last question, which is related to this pressure of the invasion of Ukraine, unfortunately, but worldwide, there is a big question right now. Can Germany survive without Russian gas? Which are the alternatives for this?
Yeah, it's a very difficult question, a very political question. I mean, of course, German economy is stable, and we are very willing to move forward as quick as possible. And I mean, it is a question of getting a solution which is acceptable for all the broad public. So for the little income and for the large income, and something which may be fine for the high income and for the politicians discussing it, which are on the high income side, and may not be appropriate for the little income. And so the solution we are seeking for is within the European community. So we try to solve the problem together, and I guess that is the right way to go. So we have colleagues around which have easier access to renewable energy and will enable us to move forward. And so I think that the political decision needs to go in this direction. Yeah, but I'm not the politician to decide. And I cannot analyze all the follow-up effects that you have when you move in one of the directions.
Yeah, exactly. We hope that things get better soon.
Yeah.
It's very important for all of us, actually. So I'd like to thank you very much again on behalf of the Brazilian Chemical Society for our wonderful lecture and discussions. And I'd like to thank Marília Vale for her assistance today, and to all of you for attending this section. Thank you and have a great day.
Thank you very much. Bye-bye.